Grab some words maybe? Yeah. I can see you lovely. Yeah. So I think let's get started. So let's see how our progress has been so far in the bootcamp. Starting on the week 1, we saw what is control. We just touched upon and got an introduction to the control systems. In the week 2, we saw the control systems more in depth, learned about new concepts like LQR and PID. In week 3, what we will be doing is we will be using the concepts that we have learned so far to build a self-balancing board in MATLAB and Simulink. And coming to the week 4, we will gain more advanced control over the board and we'll learn more advanced things in the control system analysis. So here is what I will be covering in this session. Starting from, I will be asking my board why he falls, then moving to IMU, a very important part of our board. And then we will be understanding how the feedback and PID loops works in our board and it tells us how to control its equilibrium back. And then at last, we will be balancing our beast. So I think it's time to let's get started. Yeah. So what, why he falls. So we will be diving into cute physics and maths of behind the stability of our board in the physical domain. And we will be seeing how it balances its back and how it transfers the data to the control system. So yes, cute physics and maths. Cute, no? So don't worry, won't be diving this deep into the physics and maths, and we will try to gain more of an intuitive idea behind how the physical and mathematical domain of our code works. So yes, so in the last webinar, we saw some equations like this. Can anybody tell what were the name of these equations? What was the name of the system? What basically we call this type of representation. Yeah, you can use the chat box or you can also raise your hands. Well, I see no raise of hands. So these are the set of equations that we know as that we call as state space representation of our equations. So what do we have here is we need a variable of something like this that we call as state variable. This variable will define the dynamics of a system completely, like how the board moves in all domains. And then what else do we need is for this variable, we need a set of equations that explains the relation between these variables, like how these variables are correlated and how these variables work together to achieve the motion of the board, the dynamics of the system that we have. So what we need is we need the systems of such kind for our trunk board. So let's not dive right to the board and it might get hard to begin with. So let's start with an analogy. So here you can see is a normal pendulum. So what happens is if we give it a push, then we know its center of mass is below its power point. So what happens is the gravity pulls it back to equilibrium position and the bob comes back at rest at last. But what happens now if we turn this pendulum upside down? So as you can see over here, we have our pendulum turned upside down. So now if we give it a disturbance, then what happens is gravity will try to push it further away from its equilibrium position. So what happens now is like as you can see over here, the pivot point is moving. So what we need to do is we need to put a movable pivot point and we need to move at such a pace, at such a velocity, and we need to control that pivot point at such a rate that the board can gain its equilibrium point back. The board can gain its balance back. So let's see how if we try to write the equations for it, let's see how it works. So yes, if I define T as the total kinetic energy of the system and M being the mass of the cart and small m being the mass of the bob. So this will how it will look like. V1 will be the x dot square and V2 will be the change in the x minus L sine theta and L cos theta in both x and y axis. So we now substitute the values of this V1 and V2 in the total kinetic energy of the system and we get this equation. So now we will be using a method known as Lagrangian system. So we can have two methods out here. One will be the balancing the force in all the equations to obtain the equations that we need. As we earlier saw, we need to have this type of equations. So similarly, for the inverted pendulum as well, we need to have this type of equations with us, which will explain the dynamics. So for that, what we are going to use today is what we call as Lagrangian system. So what we do in this system is we need to have generalized force in the two variables that controls our system. So as far as we are concerned for this inverted pendulum on a cart system, so we have two variables. One is the x variable, how fast the cart is moving, whereas the cart is in the x-axis, and the second is this theta variable, the tilt of the bob on the cart. So for with these two variables, we have to calculate the generalized force in each. So what we do is we just give a displacement in that particular variable to our system, and then check what are the total forces acting on it. So if we see in the x direction, then there's only F force acting on it. So the work done will be F delta x. So we have our generalized force in x direction as F. And similarly, if we do in the theta domain, if we push by a displacement delta theta, then what we get is mgl sine theta delta theta as the work done. So we get the generalized force in theta domain as mgl sine theta. So this type of equations are not what we call as Lagrange's equations. So what basically they are, they have the total kinetic energy of the system over here, they have the variable and the respective generalized force over here. So similarly for the x and theta, we now have two equations. So if we now integrate this both equations, what we have, yes, we now have our two equations that we needed that are relating the state variables with each other. But thing is, are these equations linear? Because we see we need to have equations of this form as we can see over here, x dot equals to ax plus bu and something like output being cx plus du. But if we see over here, I can just find the terms like x double dot, theta double dot, and like many more terms, which makes the system non-linear. So the problem with the non-linear systems is it doesn't mean that we can't control them, but like we can't directly apply the control system analysis that we have learned so far, the processes that we have learned so far, like LQ or NPID directly to them, and their study becomes a bit more complex. So what we need to do now is we need to linearize this set of equations that we have obtained by performing the analysis over them. So for doing that, what we need to do is, first of all, we need to calculate the steady state values to calculate the constants in the terms, and also for that, and then also we can use the Taylor series of expansion for the terms like sine theta and cos theta, and like we can go till the first derivative of them and obtain some type of equation. So for doing that, what we need is I introduce a term called fixed point. So what basically a fixed point is that point of a system, is that set of coordinates of values of the state variables of the system, for which if the system is in that state, and if we don't give an external boost of it, then the system remains in that state for as long as we keep it, as long we didn't apply an external force to it. So I want to ask you guys, for what values of x dot, theta and theta dot, our system will remain in that position for as long as we want, until unless we don't apply any external force to it. So yeah, any answers for it? Okay, and you can raise your hands and else write to the chat. Okay, I can see here is a fine. Yeah. What do you think are those values for x dot, theta, and theta dot? Okay, so let me only tell you. So for like we know the theta needs to be 0, the pendulum needs to be upright. Yes, I can see in the chat, or it should be 0. Yeah, it's exactly what we want. It's correct. So what we need to have, we have to theta equals 0, x dot equals to 0, and also theta dot equals to 0 for a system to be at equilibrium. However, x can be a free variable as long as it doesn't matter to us where the port is, but it needs to be at the stabilized condition. If we talk about the fixed point, then we talk that unless the external force is applied to it, the board remains at rest. So that's why x can be any free variable at the board will remain at rest at any x if these three variables are 0. So coming back to our drunk board, so this is somehow our diagrams of our drunk board look like. So what for getting the equations that we have derived for the as we see earlier for the inverted pendulum, if we need to get the same type of equations for our drunk board, what we need to do is we perform a similar kind of process. We just try to either balance out the force in all directions and try to obtain the equations, or otherwise we can use the Lagrangian system as we just saw. So what now we have to do, first of all, we need to define a state variable for our trunk boat. So what our state variable is gonna be like, and what we are picking is something like this. Yeah. So what are all the terms that we have over here? First is phi L. Phi L is the rotation of the left wing, and phi R is the rotation of the right wing, the angle rotated by the respective wing. And the theta is the tilt of the boat in the z-axis. As we can see over here, theta is the tilt of the boat. And then we have their respective first order derivatives to check how fast are they changing. So these are the variables that will determine the position and the dynamics of our trunk boat. However, while we are going to build this model, to build the self-balancing boat in the MATLAB and Simulink, we will be only considering its one axis motion, one dimensional motion in the translation. So for that motion, our phi L and phi R will become equal and to theta. So our only state variables for that boat will be x and theta. But however, we consider just two dimensional motion out here. As we can see over here, the boat is tilted by some angle phi from the horizontal. So this is due to the difference in the rotation of the left and right wings. So for this system, we defined phi L and phi R the separate variables and theta. And for the input of the system, what we have is VSL and VSR. So what are these? These are the voltage supplied to the DC motors that are controlling the two wheels respectively. So VSL is the voltage supplied to the DC motor of left wheel, and VSR is the voltage supplied to the DC motor of right wheel. So if we perform the similar kind of analysis that we performed on the inverted pendulum, as we see just now, so what we get is we get this type of equations that we want. This is x dot, this is ax plus bu, and similarly we have y equals to cx plus du. However, the d term is 0. That means the input doesn't directly controls the output of the system. So yeah, I have written the y term over here. So what you guys think is going to be the output of the system? As you can see through the matrix multiplication, we will be having the 3 output terms. So what you guys think are going to be those 3 output terms that we're going to give back to the system? Yeah. And any raised hands? Okay, so the 3 outputs that we will be getting back from our systems will be, first will be the yaw angle. So what yaw angle is, as I just earlier told, as we are allowing the 2-dimensional motion as well of the translation motion as well of our board. So the first will be this yaw angle, as we can see over it, which is equals to the difference in the rotations of the both wheels. So it will be equals to phi L minus phi R. So that will be the yaw angle. Second output of the system will be the x of our system, where the boat actually is. And the third output of the system will be the tilt. The tilt, as we saw, like how far the boat is tilted from the vertical axis. So this will be the output of the system that we'll be having. And now for the system, we have this equations like x dot equals to ax plus bu. So now we can apply the control systems over them, and we can just try to bring it back to the balance. Well, okay. So one thing clicked my mind while I was discussing all this. We have so many angles like theta, theta dot, phi L, phi R, phi dot L, phi dot R. So how does our boat sense all these measurements? How does our boat get to know about all these angular measurements at just so quick, at just so fast in a time? So for that, what does our boat have is what we call IMU, the tailed passive queen. So what does it do? Let us understand the working of it and how it co-works with the board to give the data regarding the angular coordinates of the system. So what basically is IMU is? So IMUs are the devices that helps us to just derive the physical quantities of the system, or the current physical quantities like its speed, angular velocity, or the magnetic fields around it. So it can have 3 types of devices with it: accelerometer, gyroscope, and magnetometer. So the IMU that we use for our self-balancing mode is what we call as MPU 6050. So what does this MPU 6050 comprises of? It comprises of a 3-axis accelerometer and a 3-axis gyroscope. and it communicates with the microcontrollers via communication protocol that is called I2C. It's basically integrated circuit protocol that works on master-slave architecture and kind of thing. So master orders the slave to work. Okay, so any doubts till now? Yeah, just any queries, any doubts on any topic till now? Okay, well, then I move forward and let us try to understand how the accelerometer and gyroscope works. So what does our accelerometer does is it measures the linear acceleration of our board. So what basically it's responsible is, well, as we see in the state variable, we had the two terms with us, x and x dot. So for finding those two terms, accelerometer is responsible for finding those two terms for our board. While, however, if we see for the other two terms, theta and theta dot, what we have is gyroscope. It just measures the angular velocity of the board. So how does this two devices works? Let's go one by one, coming on the accelerometer. So what happens is we can imagine it's something like a box with a ball in between. So what happens is it's like a vacuum system. So if we apply a force of 1G on it, then the ball goes and collides on this. We can see we have the naming on all of the plates. So if we apply this a force of 1G in the x direction, the ball goes on and collides with the ball, and the ball calculates the force being applied on it and the respective phase, and on the basis of it, it is able to calculate how fast the ball came and how fast the axis and what is the respective positions of the system is on the which the accelerometer is kept. If we move towards the gyroscope and learn about its working, so what basically it measures the component of gravity in both x and y directions, and then it calculates the tan theta from it, and for the tan theta we gain the theta of the system, and so then we have the theta of the system, then we can calculate the theta of the system. So like this, our accelerometer and gyroscope works together to serve data to our board. Okay, so now we have a board. We have our MQ6050. So let's go one by one. Our board moves. MQ6050 will detect its motion, its current state. Then MQ6050 will send that data to our board. But does our board now know what to do next? How to bring it back to the balance? I can clearly see he doesn't care, but we do have to. So what we do is we need to imply the feedback loops and the PID in the board to let the board know what it has to do to bring it back to the balance, to bring it back to its equilibrium position. So we have been reading this term from last two webinars a lot, like PID, but let us try to understand how this term actually gets implied to our board. How this actually, the three terms, the three concepts that we have learned so far, KP, KI, KD, controls the dynamics of our board and helps us in removing the errors. So the first term, P, proportional, it's basically if we have the bigger tilt of our board in any of the direction, the proportional constant will give more the constant that gives the more of the tilt, more of the push to it, more of the correction term to it to bring it back to the balance. So it's directly proportional to the tilt of the angle. The bigger the tilt, the bigger will the push from the proportional constant. Similarly, if we go to the integral term of our board, so what happens here is, as we have read earlier as well, the integral term is responsible for the steady state errors that our board has been having. So what happens is, the board is slightly off balance for the long time, it is being stabilized in that position for long. Let us take an example, like if our board, instead of being balanced at the theta equals to 0 degree, it gets balanced at the theta equals to 4 degree for a long time. And it's like slightly tilted to the vertical for a long time, and it gets at equilibrium at that state. So what we now need to do is we need to bring it back to the 0. So what term do we use? What constant do we use increase for it? We use the integral constant for it. Similarly, for the derivative constant, what it does is it prevents our system from like overreacting to the error that it's receiving. It's like breaking the system to bring it back to the equilibrium as fast as it can, and prevents its like oscillations over the steady state value. So we now have our PID signals. PID signals, but how does our PID signals communicate with the motors that is rotating our cart? How does it send those signals to it, and how does it knows that how much it has to rotate to bring the cart back to balance? So for that, what we have are PWM signals. So what basically are these signals? It's like we are switching off and switching off switching on, switching off very really fast, so that the average value is equal to the value we want our motor to rotate at. So what basically in a DC motor, it rotates on the basis of the average value that it is receiving. So that's why the PWM signals comes to the help to us. So what we actually do is our PID output will send something known as PWM duty cycle. So what basically a duty cycle is like the average of the values if we take over the time. So like the time it was on plus the time into 1 plus the time it was off into 0 divided by the total time. So that is what we call as a duty cycle. We can also represent it in the form of percentage by multiplying into 100. So the higher the duty cycle is, the higher it means the PWM will be, the faster will be the speed of the rotation of the motors. So how does it control the wheels? So the PID will give the PWM signal as the output to it, and the PWM signal will also contain the direction of it. As if it's a positive signal, then it will rotate the wheels forward. If it's a negative signal, then the wheels will rotate backward. And if it's zero, the wheels will stay still. And also the value of the duty cycle will control the speed. How fast the duty cycle, how more the duty cycle is, the faster the wheels will rotate. Plus, the PWM also ensures smooth and analog-like control over a system. So if I show you a bit of simulation on how the duty cycle changes, so we can see over here. So if I vary the duty cycle with the slider, you can see the width of the pulses is varying, and with the varying width, we can see the average value of the PWM signal is varying over here. So and you can see the duty cycle value over here. So if we increase it to something around 50%, then you can see the half of this, we can get about the half of the average value. Similarly, if we go on to full, it's like we have only the 1 as a signal, and if we go to 0, we have only a 0 as a signal. So this is how our PWM signal operates on the basis of duty cycle that we are giving to it. Okay. So moving forward. So we now know how the PID gets the data to the motors to rotate accordingly as it wants it to be. So let's understand it in a cycle. So what happens is we give the disturbance to our boat. That disturbance will cause the tilt in our boat. Then the tilt will be served to the MQ6050. And now as the MQ6050 has that tilt, it will calculate the error based on it. And now we have our PID, it has the correction factors. On the basis of error, it will calculate some correction factors, and then it will, through the PWM signals, it will serve to the motors. But one thing is breaking in this loop. That is, how is this error that we are calculating to the MQ6050 is being served to our PID controller? How is that error being served to the PID controller? How does error that reach the PID controller? So where is the fix? So for that, we meet our spin doctor, the angular feedback loop. So what happens in it is, first of all, we have our desired value. That is, for our case, its port angle needs to be 0 degree. Then we have the measured value that we receive from the MPU, the current state of the system, the current angle, the current tilt of the port. And then we subtract those two values, we get our error. On the basis of the magnitude of error, we know how strong the correction factor we need to bring it back to the balance. And also on the basis of this signs, we know that where it is tilted, like if it's positive, it's tilted forward and we need to push it backward. Similarly, if it's negative error, we know it's tilted backward and we need to push it forward. So this is how our angular feedback loop works. And this is how the angular feedback loop feeds back data to the PID. So let us see what happens exactly at each microsecond. So what happens is MPU gets the angle and angular velocity data. Then it calculates the error and it's feed it to the PID through the angular feedback loop that we have. Then the PID will give the motor commands on the basis of PWM signals that it has calculated through the correction terms. And then the motor will rotate accordingly and the boat will bring back to the balance. So this feedback loop will restart in every 10 microseconds. Yeah, that's so fast, no? So yeah, any doubts still here in any of the components and any of the systems that we have done so far? So this PID and all things we have discussed in the previous webinars as well. So in this webinar, we will see their implementation to our board. So yeah, any doubts still here? Okay, I see no raise of hands, so let's move forward. But balancing isn't just about angles. So, like we have been calling till now, self-balancing board. The name is not justified if our board keeps on translating, even if we have its angle to be zero. So what we now have, like we have our board being balanced at the equilibrium position, but we still have its x dot moving. We still have our board translating. So that's not how we want our self-balancing board to behave like. So for that, what we need to introduce is a translational feedback loop as well in our control system. So what that loop will do is it will tell that where our boat actually is in the translational axis in which the boat is translating and how fast it is moving in that translational axis, like how fast the x dot is x is changing, the x dot is varying in that axis. So this data will then be served to another PID controller, and on the basis of this data, on the basis of this error, translational error, the PID will control its the correction terms that it has, and then it will send those signals back to the actuator. Actuator is like the motors that are rotating the wheels. So let us just see how this full feedback picture works. So what happens is we have an MQ6050 sensor. It will tell all the data to our board, starting from x dot, theta dot. Then the error will be calculated, which will be the desired minus measured values. And then we will have a signal split into two different loops. First is the angular feedback loop that we have seen, and second is the translational feedback loop. So for both the loops, we have the separate PID controllers. So for the angular feedback loop, the data theta and theta dot will be served to it. And for the translational feedback loop, the data x and x dot will be served to it. Then what we do, we just multiplies it by a 0.5 factor in the both the loops. So why basically we are doing is it's just like more of a normalization factor, as we don't want our system to overreact to the errors that are coming from both the loops. So we just multiply it by 0.5 to just normalize both the factors together and serve it, and then we add those two factors and then serve it to the actuator. And the motor rotates according to it to bring our board back to balance in both angular directions and both translational directions. But also we need to have one more thing over here that we call as converter. So what is its role? So as we can see over here, we have the angular values being transferred to the angular loop, and the translational values x and x dot that have their units in like meters being transferred. So we can't directly add two different quantities, meters and radians. So what we need to have here is a converter which converts the radians to meters, and then so that we can add those two correction terms together and can serve it to the actuator. Okay, well, it looks like we have fixed most of the pieces of puzzles for our self-balancing board. So is it time for the final boss level? Yeah. So now we balance our beast. So I request you all to open your MATLAB. We will be now balancing our beast in the MATLAB. Yes. I already have my MATLAB window opened with me. So yeah, this is how the MATLAB window looks like. So one thing before I start is in the last webinar, we just got a quick intro to the MATLAB and Simulink and how we introduced the control systems, the control loops to it. And we saw it in the assignment as well. So what different we will be doing today is we will be using a feature of Simulink that we call as Simscape. So what that helps us in it allows us to like perform this to simulate our system to have our body with us to import the solid elements to our Simulink and to just visualize how that solid elements are working with the control loop that we are applying to it. So for that, you need to have add-ons. If I show you mine, you need to have these two add-ons with you. First is Simscape and second is Simscape Multibody with you. So if you guys have not installed it yet, so you can install it from here. If we go to here, this explore or add-ons option. So if you click to it, you will have a page open over here. You can search this two add-ons over there and you need to install it. Okay, so now next what you need to do, you can open the command window over here and you need to type this command over there, smnew. Yeah, smnew. You need to type the command and press enter. Yeah, I wait for 2 minutes for you guys to follow. If you guys any doubts, we can cover it till then. Yes. Yes. Any doubts, any queries till now? And any of the content that we saw in the slides? And how the things correlate and who work with each other?
Excuse me.
Yeah.
Why do we not measure the angular acceleration and the linear acceleration? Why do we only use velocity and position? Is there a reason?
If we are just able to normalize its velocity back to it, so we don't need to have the acceleration also being normalized. So if we are just bringing its velocity back to zero, so it is, of course, that the acceleration is also gonna be the zero. So we are just also measuring the change of the velocity, like we are having the x dot as well as a one of our state variable. So we are also measuring like how fast the x dot is changing already. So if we are just able to balance x dot as well to back to the zero, so we are actually balancing the acceleration as well back to the zero. I hope you got it.
Okay, so we're just measuring velocities at different times and indirectly calculating the acceleration, and
Yeah,
then
yeah, yeah,
okay,
exactly. And then getting it to be back to zero. Okay, so
gotcha.
if you type this command in the command window, smu, and press enter, then a page like something this will open up. I hope it does for everyone. Any issues? Yeah. So let us remove these blocks. Simple. Turn on. Yeah. So this is how a Simscape interface looks like. So what we have here is, what new we have here in the Simscape is, we have this three new blocks with us. So what are these three blocks? Let's go one by one. So first is the solver block. So what is this used? It is used if we need to introduce some functions in our loop. So we can use this block there. Second is the world frame. This is one of the most important blocks in the Simscape. So what does it do? Is this something like a reference frame? It introduces the three axes to our simulations. Like it introduces the 0, 0 coordinates. Then if we connect those blocks to it, they are going to be at the 0, 0 coordinate. So it introduces the three axes to our simulations. And then we have this mechanism configuration block. It helps us to define the gravity data root. So if I go back to the board that we are trying to build, then this is the board that we are trying to build. So I will be starting by building the wheels of it, the cart portion of our board. As you can see, those two wheels over here. So we will starting by doing. So going back to our MATLAB window, if you double click at any space, then this thing of search query box will open up. So what you need to type over here for our wheels, we need to import the cylindrical solid first. So you can type over there. Yes, this is the block that we want, cylindrical solid. If you double click on this block, yeah, this type of box open up where we can change the parameters of it. So try to follow along with me in the values. Radius, we gave it 32.5 millimeters. These are pre-calculated values, which will help us to visualize our model easily on the basis of the inertia and mass values that we calculated last. So just try to follow up with me on this part. We give the length to be 12.5 millimeters. Yes. And we have to give it mass as well. So here from the inertia, you can have to go here and change this density to mass and assign the mass to be as 50 grams. Yeah, for the wheel. Also, we can change the color of it. So I think black looks the best for the wheel. So if you press the refresh over here, the graphic that is being shown here changes. So yeah, if I zoom in, this is something how our outer wheel looks like. But also now we have to give its inner wheel as well. So what we now do is, what you have to do is you can hold the control and then drag this block over here. So what happens is we just duplicate this block with the similar properties. So so that just we can differentiate it from the outside part of the wheel. I just change a bit of its values as just 30 or yeah 12.7 something. Yes. So that we can actually just see it and the color to be, let's say, yellow. If we refresh it, this is how the inner part of the wheel looks like. So now let us connect it to the world frame and see how does they look. So if you press Control plus R, you will be actually able to rotate your block. So now with the left click, you can just give the connections to it and rotate this block as well. And with the right clicks, my bad, the right click, you can just give them back the connections. So if you press Control plus D, simulation window will open up. You can see it's defining over there. Yes, this is our simulation window that will open up. So if we see this, so this is somehow our wheels look like. The inner wheel and the outer wheel together. This is how our wheels look like. Okay, so crossing it. So to make it look a bit less clumsy, what I do is I just create something creates a subsystem out of it. It's just basically we are grouping them together in a smaller block, and I name it as, let's say, left wheel. So we now have our left wheel with us. So again, I duplicate by holding Control, and I name this another part as our right wheel. Yeah. So I just connect it as well to the reference frame. Okay. So if we go back to our board now, here. Okay, so if we go back, if we see it again, then we have the wheels, but we also need to have a rod in between connected these wheels together. So for that rod, what we need to do is we go back to our MATLAB. Yeah. And what we need to import now is another block, which is we call as brick solid. Yeah, this one. So anybody, any queries till now? Or anybody got stuck anywhere? So if we again double click it, this we can change the dimension bit as well. So we keep it as 1, 1, 20 as the respective dimensions in all three axes, and the unit to be centimeters. Yes, and we give it color as black, maybe. Yeah. Okay. And also we need to specify its mass as well. So we again change the density to mass and defines its mass as 100 grams. Yeah. So if we again push refresh, so this is how our rod looks like. Okay. So let us try and see how, if we connect these things together, how does this thing look in the simulation window. Again, I press Control plus E, the simulation window opens up. So what happens is, as you can see over here, I have connected all the three blocks to the reference bit. So what does it exactly mean? All the three components are at 0, 0, 0 position. So you can see over here as well, we have the two of the wheels that are like overlapping with each other, so that so we are not able to differentiate them from each other. And then we have the rod as well in between. So what we now need to do is, this is our z-axis, this one is a z-axis. So we need to translate this wheels that we have, one to the this end to the of the rod and other to the this end to the rod. So what we need to do is we need to make this wheels move a translation in to this different ends of this rod in the z-axis. So to do that, we have a block named as a result transform block. So basically what this block does is it helps us to keep the different elements of our body together throughout the simulation. It just like fixes those components together. So I introduced this result transform for both the wheels, left and right wheel. So one more thing, if we see this result transform, it has two ends. One is F, one is named F, and one is named B. So what are these? This is the follower, and F stands for follower and B is the base. So always remember, base needs to be connected to the reference frame, and base always of all the blocks faces the reference frame. Whereas follower is the block on the basis of which the result transform is gonna perform the transform to. Like we want our wheel to transform, that's why we are connecting the follower to our wheel. So always remember while connecting the rigid transform block that the F needs to face the block that we want to transform, and B needs to be connected to the reference frame. Needs to be facing the reference frame rather. Okay, so if I double click it again, so what I now want is I want the translation of a wheel in a Z axis as we saw earlier. So we go to the method, we want a standard axis translation in plus Z of how much we want it to be of 10 centimeters. As we saw the length of the rod was 20 centimeters. So we need half of it, so 10 centimeters. Okay, so if I now try to visualize it again, then yeah, we can see one of the wheels moves to that end of the rod. Now we want this field to go in the minus Z by exactly the same value. So what we do is I again duplicate it and put it over there. And instead of say 10, I put minus 10 over here. Okay, so if I again go to the simulations, yeah. So we now have a cart with us. Let's see over here. So I go back to the board. So we have this lower portion, the cart, the wheels with us. So what we now have to build is this upper body, this body that we call as chassis. So now we need to build this upper body for us. So let's go back to the MATLAB. Yeah. So again, what I do is I just group them together to create a subsystem again. And I name this subsystem as my cart. So till here, anybody has any queries, any doubts on any of the step, on any of the blocks if you wanna clarify? Yeah, you can raise your hands or put the queries in the chat. Okay, I see no queries. So now what we need to build is it's the upper body. So for the time being, you just delete it and I just select this card and comment it out from the scene. What does it actually mean? We are just having it with us only, but we don't want it to run in the simulations window for us as of now. So now as we have to build our upper body. So upper body, what the upper body has in the board for us, it has this 3 plates, as you can see, the light pinkish shade plates that we have that this board has. There's 3 plates over here, and the 4 rods that are connecting these 3 plates together. So let's start from building the plates first. Yeah. Again, I'm going to double click it. The plates needs to be cuboidal, so we need to import brick solid. Again, double click it. We need to specify its dimensions as I gave it as 18 in length in X, 8 in breadth in Y, and a small extension is Z as 0.3, all in centimeters again. Yeah. And again, we need to change this to mass. We need to define its mass as, I do it here as 1/4 of a kg. And then we can also specify its color also to it. So you can see by default it's gray, but on the basis of poll that we had a winner. That's the red, the Iron Man red. So we assign that color to the plates. So let us see how does it look. Cool, no? Yeah. So this is how our plates gonna look of the upper body of our board. Okay, so we now have the plates with us. So we saw that we need 3 plates for it. So let me just first connect this plate to the ground frame. Yeah. Okay, so yeah, let's connect to the reference frame. So we now need to have 2 more plates like this. So I again control and duplicate these plates. Yeah. Okay. But now again, we need to introduce rigid transform between these 2 plates to hold them together in the specific geometry we want them to be. So I import the rigid transform block again. Yeah, between them. Again, make sure, yeah, I rotate it, have it properly. Again, make sure we connect the follower to this plate and base facing the reference frame. So we now have a rigid transform between these 2 plates. So these are the 2 bottom plates. So between the bottom plates, we want our length to be less. So between these two plates, we have our length in the in the direction to be as 10 centimeter, and in between the upper two plates, we need to assign the distance as 25 centimeter. We are going to assign the distance as 25 centimeter between the upper two plates. This is done like we have this unequal distribution, so as we can keep the center of mass of our boat at a lower position, and it will help the stability of the boat as well. Okay. And yeah, we'll get the same here. Yeah. So what we need to do for it, we need to have a translation again in the standard axis, in the z-axis of 10 centimeters, as we want the distance between the bottom two plates to be 10 centimeters. And now we have our two plates together. We also need to connect the third plate. This one, I rotate it. I copy the result transform block. I rotate it as well. The follower facing the plate. Then connect the follower to the plate. Yeah. Yes. Okay. The base, the reference frame that we have over here. So between these two plates, we want the distance to be of 25 centimeters from the bottom plate. So now if we try to see these three plates in the simulation window, this is actually how they look. Yeah. Yeah, these are the three plates. We have the 10 centimeter distance over here and the 25 centimeter distance as of total. So we now have the plates with us, but our board needs this 4 rods to connect these plates together at 4 of it, or at 4 of their corners. So we now build the rods for our board. So I close this window. Yeah, we have this MATLAB again with us. So for that, what I need to import is again cylindrical block. Yeah, cylindrical solid block. Yeah. What dimensions do I need to give to it? It's like we need to give a radius to be 5 millimeters. We need the rod to be small and length to be 25 centimeters. As we see, the distance between the bottom to top plate is of 25 centimeters. So the length to be 25 centimeters. And again, we need to change its mass to be around 1/16th of the kgs. Yes. And also we can change its color. So I think can give a bit goldenish color to it, as we want our Ironman color combination for our board. So let's see how this rod looks. Okay, so this is one of our rod that we have with us. So if now I connect this rod directly to the world frame, let's see how will it look. Okay, so if I connect it directly to the world frame, I can see the board initially by default gets positioned as the 0, 0, coordinate. So it's at the center of the plates, but also bit down in the z-axis, as we can see over it. It's the z-axis, the upward axis that we have. So we have a displacement, this correction displacement that we need to correct, and also it's at the center, so we need to push it by half of the length and breadth to all the 4 diagonals of the of our plates. So for that, we again need to have a rigid transform between it. So another block created. Again, take care that the follower is connected to the rod. I double click the result transform. So what we now need is, till now, what method we were using the translational was the standard axis method, as we wanted the translation to only occur in a single axis. But now we can see, is it the center of the rod, was it the center of the plate? So we need to move it in all the 3 axes, in the X and Y to bring it to the corners of the axis, also in the Z to shift it upwards so that it fixes, it matches exactly with the height of the 3 plates. So for that, what method we use? It's this Cartesian method. It will help us define the translation in all the 3 axes instead of having 3 rigid transform blocks introduced separately with the standard axis method. So what values do we give to it? We need 18 by half and the length to be shifted -1. We doesn't want it to be exactly at the corner. Also, for the breadth, we do as 8 by 2 minus 1. And for the length, I calculated the overshoot of the length. So it comes out to be 25 by 2. Yeah. So all this in centimeters. Don't forget to change the value units of them. So if I go back to the simulation window and see, so we have successfully moved the rod back to the top right corner of our plates, and you can see as it's correctly at the corner, and we have no overshooting in terms of its height in the z-axis as well. Similarly, we now need to have 3 more plates at the 3, 4 corners to complete the upper body of our boat. So I close this window again. I just select this box and I move them a bit far so that I get some breathing space to put the blocks. Okay. I just rotate this block. Yeah. Okay. So now what we can do is I just select this, press Control C, and yeah, can copy paste here as well. You can press Control C, press Control V. I connect this one here, smooth it a bit. Yes. Okay. I need more. So again, Control plus V. Put over here. I need one more. Again, Control plus V, and I just okay. Need just connect it better. Yeah, I connected and just I move it over there so that it looks symmetrical. If we see, yeah, yes, and we also connect this one as well. So, so all these rods are again gonna be at the center. If we see, we have not done anything. Okay, so we need to put the values of digit transform first. So as the digit transform was copied for all the blocks, you can see all the 4 rods are just coinciding over here at the same corner. So what we now need to do is we need to change the parameters that we gave to the digit transform earlier. So how we do that? So think of it as it has we have all the rods at 0, 0 initially in the center of each of the rectangle that we have. So we now need to move it to the 4 corners. So if one of the corner is x, y, then the 4 quadrants, the other corners will be like minus x, y, the other will be at x, minus y, and the last one will be at minus x, minus y. All to the displacement that we want in the z-axis remains the same as 25, 2. So 25 by 2. So what we now do is we change this coordinates one by one. So first of all, I do it as minus x. We have already done the plus x plus y portion as we have moved it to the top right corner. So this will be the minus x plus y. Then for this plate, we do it as plus x minus y. And for the last plate, we just reverse the signs for both x and both y. So that we have our rods exactly at the 4 corners as we want them to be. Yeah. So if again I press Control plus D and if I visualize the board now, just put out. So yeah, and I can see the 4 rods are exactly at the 4 corners as we want them to be. And you can see there's no overshooting as well from anywhere, and we have the rods exactly at the 4 corners if we want them to. If we go back to the board and see, so we now have the lower cart portion of our boat with us with the 2 ways connecting with the rod. And we now have also built it the upper body, the upper portion, the chassis portion as well of our boat. So what we now need to do is we need to connect this boat together. So let's do it. So yeah, again, what I do is I create a subsystem of this whole to make it look a bit less clumsy. Create a subsystem. So like it. Smooth it out, and I name this portion as my chassis. Yeah, just wait a bit forward over here somewhere. Yeah, so now I uncomment my cart portion that I had earlier. As you saw in the simulation, the cart portion was not showing up. This was because we commented it out earlier and we didn't wanted it to like show errors, like we have not connected the reference frame, so we didn't wanted it to show errors in between when we try to build our chassis. So I connect my right click connect the cart, chassis in cart and chassis together, the ground frame. Yeah. So we now have our chassis with us. We now have our cart with us. So let us see how initially they are placed with each other. Okay. So this is how they are placed with each other as of now. Is it's a 0, 0 coordinate. So they both are at that as of now. One more thing before we start moving our this chassis and cart components together to fix them together through the axis. One more thing, I want my gravity. By default, it's in minus z, but I want for the simulation, I want my gravity to be in minus x. So you can just copy in this, give it a 0 and change it to minus x direction. So it like necessary. So you guys just complete it to have the perfect simulation. So we need the gravity to be in the minus x direction instead of the minus z direction that we have by default. Okay. So if I go back to the simulation window. Okay. So what we now need to do is our boat is, if you can see the upper body, it's like standing upright in the z axis. But if I go back to our boat, what we need is we need our body to be upright in the x-axis and to be facing the z-axis to be translating in that. So what we need to do now is we need to perform certain z transform again, but now the z transform that we perform are going to be a bit different from what we have been doing till now. As if I import the z transform block here, yeah. So what we did till now, we used this feature of the z transform. We translated our components to different positions, and it just fixed the things. But now what we actually need to do is, if we see that simulation window, it's facing in the Z. So I need to rotate my upper body such that it faces, yeah, as we can see over here, it faces Z axis and it stands upright in X axis. For that, first of all, use another transformer here. So I need to perform some rotation. So what kind of method I use for rotation is what we call as a rotation sequence method. So what basically happens in it, we define a sequence like here I defined my sequence as, let's say, y, x, z, and I give the angles to be 180 degree in y and then 90 degree in x, let's say. So what happens is in the rotation sequence, so what it's going to basically do is it's going to rotate our body first by 180 degree in Y, followed up by rotating in X by 90 degrees. So it's like it happens in a specific sequence that we are applying to it. So if we see why we are doing it, so instead of applying it as of now, wait, it just got applied. So wait. Yeah, if we go back to the simulation window that we had over here. So if we see the upper body, we need to rotate it by 90 degree along the y-axis that we have over here, and then turn it by 180 degree through the x-axis rotation to bring it back to be facing the x-axis. So if we do this transformation, if we apply this, yeah, that's the apply option, and we again see this. How does this look? Yeah, we just maximize this window. Okay. So what we now have, yeah, if you can see, yes. So if we see from here, what we now have is we have the chassis to be in the y direction, to be upright in the y direction. We want them to be in the x direction. So again, we need to perform another transform to make it back there. So let's check extension once. I have the y x z. Oh wait, yeah, was not exactly how it went for it. Wait, yeah. Okay. If I now see it, yeah, now we have it together. So what I did was like, let me just go it back and put it to 0, 0, 0, and then explain you what happened exactly. Yeah. If I do not rotate it at all, and let's see how it was exact earlier. So it was like this. It was upright in the Z axis. like this. We had it upright in the z-axis. So what we need to do now, what we were supposed to do now, and through the y-axis, we wanted the rotation to be at the 90-degree first, so that it rotates by the 90-degree and facing the z-axis at the upper portion, as we wanted to be facing the z-axis in the translation. So we wanted to rotate it by the through the y-axis first. If we go back to simulation window by 90-degree, and then wanted to rotate it to the x-axis by the 180-degree so that it translates in the z-axis. So if I apply those parameters now to it, I just reverse the values for y and x. So you can't mess up with the sequence that we are rotating it. So that's why the sequence becomes very important. And that's how the order of rotation is going to happen. So it's 90 and 180. If I do it now, and if I now visualize it, so we now have a board standing upright, but still the position, the one thing that still is not good is like it's we have the gravity in -x and the boat is facing -x. So typically we have gravity facing upwards. So this is what we want for our self balancing boat is, as we see earlier, we need an unstable equilibrium. So the gravity needs to be downwards so that it pulls away, and we need to apply the control system to bring it back. So one rotation that I want is I want the system to be rotated 180-degree in x to face the positive x again. And one other thing that I want is I want its translation through the y-axis. So its rotation through the y-axis so that it faces the z-axis for the translation instead of the y-axis that it's facing right now. Because if I see this picture back, we had it translating in the z-axis, and it's being standing upright in the plus x-axis. So again, we need to perform one more rotation for it. I just copied again. So what kind of rotation we now want is, we want it say x-y-axis only. We want the rotation. Yeah, this is exactly what we want. Actually, we want the rotation in x by 90-degree first. If I go to the simulation window back, I want through the x-axis, we want the rotation to be 90 degrees so that it faces the z-axis back for the translation. And then we want then again we want a rotation through, as we can see, through the y-axis by 180-degree. Why so? So that we can have a boat back in facing itself in the plus x-axis, and the gravity pulls it down instead of helping its equilibrium. So yeah, I apply this, and I again the simulation again open the simulation window. So yeah, if I wait out, and if I see it, so if you can see the axis over here, it's standing upright in the x-axis, it's facing the z-axis, and if we see the perpendicular direction, it's the y-axis. It's exactly how we wanted a board to be. If you see over here, we want it to be upright in x, to be translating in z, and the y-axis is the perpendicular direction. So this is how exactly the board looks like as of now. So we are done with the part of the arranging the different pieces that we have made so far. We are done with that part. So we have now arranged our board together. So yeah, this is how our board looks like. But now what we need to do is we need to provide the degree of freedom for the motion to take place. So we saw earlier, so there are just 2 degrees of freedom for our system. First is like the angular degree of freedom for the theta and theta dot for it to rotate like a bob. And secondly, we want the translational degree of freedom for the x and x dot term so that it can just move and translate as well in the z-axis, as in the case of ours, as we have it facing the z-axis for the translation. So we need to import 2 blocks. So till here, does anyone has any doubt, any query over any block, anything? If anybody got any stuck anywhere, so just try to understand how I am building it. And at last, we will be also the recording of the lecture will also be accessible to it. So you can just follow up later on. But as of now, just try to understand how the things are working, how the rotations and this digit transforms are bringing the pieces together, and how we define the joints and the control loops later on. So let's see. So yeah. I introduced 2 joints as I was talking about. So first is the revolute joint for introducing the rotational degree of freedom. Again, it has two ends, follower and base. So make sure the follower is connected to the chassis portion and the base is facing the reference frame portion. And yeah, we have the revolute joint over here. The second joint that we want for the translational degree of freedom, it's prismatic point. It's this one. This one will help the translational degree of motion for us. So now this is how our board looks like, and it looks like we have completed our board completely. So let us check how does it looks like if we apply some force to it, some external force to it. What I does it, I import another block. It says external force and torque, this block. So I import this block. I just rotate it again and connect it to the third plate. I'm applying the force to the third plate, the topmost plate of my board, and I double click it. I want the force to be applied in y direction, and I give the force to a step function. Yeah, import a step function out here. I rotate the step function and double click it, and what values do I give to it? I want at the initial 0.01 second, I want my initial value to be 1, and later on it can be 0. So I'm giving a push of, let's say, 1 Newton to it initially for the 0.01 second, and then it goes back to the 0. And the system tries to stabilize itself. Okay, I apply it and close this window. Okay, but now if I try to connect it, it shows it's not able to connect. Can you guys guess why it's happening? Why I'm not able to connect it directly with the force that we are giving it? Any guesses? Yeah. Any random guesses are also allowed, like there are no marks for it. Yes. Anyone, any guesses? Like what is the issue between connecting these two together? Okay, so let me show you what basically is happening is. So while we are working in the Simulink, we have two type of signals with us. One as we say as Simulink signal, and one as we say as physical signal. So the force we are applying is like we are giving the physical signal to our system. We are giving the physical quantity as force to the system. But the step function that we have, the values that are being given by the step signal, it's like the Simulink signal being provided to the external force block. What external force block needs is a physical signal on how much force it wants to be applied to the board. So what we need over here is Simulink to PS converters. So we have this two type of converters. This one is Simulink to PS, another is the vice versa of it, the PS to Simulink converter. So if we try to connect, yeah, let's put this one here only, Simulink to PS. As I said earlier, I need the Simulink signal coming from it to be converted to the physical signal to be given to the force block. So I just rotate it, yeah, and I connect it with this, and another end to this. Yeah, just for the time being. We'll come to our use later on. So I now have the force being applied by the signal to the third plate. So let's see how it will look in the simulation window. I just get it like this. Also, like you doesn't need to get it upright again and again. So you can just save it from here. It will just save its configuration here, like how it's sending, and you just don't need to change it again and again. Update it. So if I run it now, okay. So can you guys see this? Our boat as of now is rotating like a normal pendulum under the action of the gravity, as we have not introduced any control loop to it. So it's acting like a normal pendulum. It's a 10-second frame. So we see what happens in 10 seconds. What more we can do is, let you visualize this, we can introduce some damping. If we double click the revolute joint, go to the internal mechanics, we can introduce some damping, some friction to it so that we can see a bit less oscillations, and we can just actually see how it actually acting like a pendulum in 10 seconds. Because we have a frame of time, 10 seconds only. If I introduce, so yeah, as you can see, it just balances out like an onward pendulum in the downward position. So what we now need to do is we need to introduce the control system to our loop, the angular feedback loop, as we saw earlier in the slides. So for that, if I double click again anywhere, I need to import the PID block. Yeah, PID block, this PID controller block over here. Yes, let's see where we have the PID controller block. I just move this thing a bit fast so that I get a space. Okay, I rotate it. Yeah. So what now I want is I want my Revolute joint to sense and give me the current position of the chassis. The current position, what I basically mean by position is the current tilt of the chassis. It gives the angle of rotation and degrees, how much the chassis is being tilted. So now, uh, but have as the angle as it's giving to us is in degrees. So what we now need to do is we need to convert it back to the radians to be so that it can be served to the PID. So we have to insert a gain block. Gain block is just like a multiplier. As we saw the feedback loop earlier as well. It's like multiplier rotated. And I give it as a value as 180 by pi so that it can, yeah, it, yeah, so that it can be, we have the units as the radians over here. I connected to it. Yeah. Yes, like this. Okay. And I want my prismatic joint to give the force. So actuation, we go to actuation. We want the force as we have here is as none, but we want to apply the force based on what it is getting from the PID system. So I want the force to be provided by the input and the motion to be, of course, to be actually automatically computed on the basis of force that we are applying to it. So, okay. So if I now try to connect it with this, it doesn't connect again. So anyone, what is the fix of this issue? How I'm gonna connect it now? Anyone? Yeah. What is that thing missing? Why it's not being able to, why we are not able to communicate the position to our gain multiplier? Yeah. Anyone? Like I just told, we need a separate block for it, which will help us to communicate the position to the gain multiplier, which we somehow can't connect directly. Yeah. So anyone who's gonna answer can use the chat, can use your mic and raise hands. Okay. So, well, I see no one. So what, as I earlier mentioned as well, if we, when you are applying the force chassis, we need a converter to convert our signals so that the two ends can be connected and we can give the exactly the signal that our blocks want. So what we have the physical signal coming from the Revolute joint as a degrees of rotation of the current degree of rotation of the chassis. And what we need to give it to the gate multiplier is a Simulink signal so that it can work on it and it can then serve it to the PID signal. So what I import is PS Simulink converter and okay, I rotate it. And now I connect the output that is coming from here, the position output that is coming from here to this, and then connect the other end to the gain multiplier. Okay, similarly, now the output of the PID will be a Simulink signal. And if I try to connect it again, so again, it doesn't connect. So yeah, can you now tell me what type of signal converter I want? I want PS to Simulink or Simulink to PS? What type converter now I will be needing to connect the PID to the force end of the prismatic joint. Yeah, anyone? Also, you can share your queries or doubts if you have any so far, understanding how this system has been made so far. So here what we are doing is we are just implementing the angular feedback loop as we saw in the slides so that we can serve the data of what's the tilt of the chassis is as of now to the prismatic joint, which will then give the force accordingly to the cart and chassis system to bring it back to the balance. So, as I told earlier, we had the conversion over here, which converted the physical signal coming out from the revolute joint to the Simulink signal being served to the PID block. But now we have the Simulink signal coming out of it, and we need a physical signal to be served to our prismatic joint. We need a physical signal to be served with the prismatic joint as a force. So, what we need now is a Simulink to PS converter for us. Just drag it down, I rotate it, I connect it with it, and I connect the force input to be served from the PID, like this. Okay. So I think we have completed the feedback loop. So we have the position input coming from here. It's been converted to Simulink signal. It goes to the gain multiplier, which converts its degree back radians, and then those error is being served to the PID, and the PID as the we want the tilt to be 0, so we can directly serve the angle. How much the angle is? If it's 10, 10 minus 0 means 10 only. So we just directly serve it to the PID as our error. The PID will then have the correction terms will serve to as the force input to the prismatic joint. So also we need to specify the units once. We want the output signal to be, it is default by inherit. So it can inherit the value that is coming from the block, but still, oh, sorry, not the newtons. I want it to be as the radians. Yeah, radian system. Okay, and I want the force that it is serving being the newtons. Yes. Okay, so let us now see how our chassis will react for the force that we earlier applied. Yeah, we can see our chassis is like fairly stable now. It's not like the rotations as this showed earlier. We saw it rotating like a normal pendulum, but our chassis is fairly stable now. Let us just import another block like scope, as we saw in the last webinar as well. This block helps us to visualize the data of the error. Will help us to visualize the data of the error that is being served during the simulation. So yeah, connected. I run the simulation again. Yeah. Then I go back and check my data on the scope. Okay. So can you guys see it's like showing a bit of oscillations around 0 before just like finally going to being stabilized at the 0. But we can see the small oscillations are still there, and the time frame is small. Sample time frame is very small. 10 seconds is not stabilized as of now in the given time frame. So what we now need to do is we need to change the PID values for it. If we double click it, we have this type of values with us. So you can see it's just like overshooting, overreacting to the force. We can see some smaller oscillations still having in scope. So we need to change its derivative by right. Look at it now. And I run it again from here. Yeah, the oscillations are far less. I go to the scope and see, yeah, you can see it's through the derivative gain that we introduced, the oscillations are far reduced, and we have the stabilized value over here. Okay, but the value that we gave to the third plate was like very little force. So what if now I just go to the chassis and remove this force that we applied now, and instead of just remove the signal here, and instead what I do is I give it an initial error to a step input. So what I do is I import a step block again to the model. Yeah. And again, I want in the initial second, what I give is I give the error as 10 radians. So what does it actually mean? Even through the error, the actual position, it's 0 degree. I give the error in the initial 0.01 as 10 seconds. So that error is will be served. The force will be applied accordingly. The port will tilt. Then that value will again be added, will be again be given to the angular feedback loop. But after that, we want the final value to be 0. Then again, the value coming from the steps will become 0. And we will have only the angle that is coming out from the angular loop. So what will then happen is the boat will try to stabilize on the basis of this current position of the boat. So are you with me till now? Any doubts still here? like what I'm doing by. So I have my step signal, and also I need my step signal to be subtracted from the current angular state that we are getting from the revolute joint. Let's just move this thing a bit. Right. Okay. This is the sum block that we use. Just rotate it. Yeah. And if we double click it, I want uh, my signal coming from the current state coming from the revolute joint to be to have the positive sign, and the step signal coming have to have the negative sign, so that later on when it becomes zero, the negative has to be subtracted from it. So if I connected it to is this end, I connected the positive end to the signal time received from here, connected the PID to give input from here. Okay. So if I just give it some values over here, it's one, and we just see how does our system apply to it now. And something else. Okay, so let's run the simulations and see. Okay, we can see initially we saw some oscillations of the board due to the initial 10 radians error that we introduced in it, but finally the board brings back to the balance. So if we go back and check our scope again, so yeah, you can see initially there was a lot of error on the basis of 10 degree step input that we gave it, but coming to the nearby, as we came nearby to the 10 degree mark that we have, the board fairly stabilized. So this is how I gave the angular feedback loop to it. But if we go back and see our oscillations or simulation again, then what happens is again the same problem that I discussed in the slide is coming. If we see the orientation, the tilt error has been removed, but our board is still translating in the axis. As we see over here, the tilt is now fixed. It's at equilibrium, but the boat is still moving in the z-axis. So for that, what we need is we need to introduce a translational feedback loop to our control system. So well, that's going to be our assignment as well for this week. So that's on you guys to build. So this is how, and also the tuning of the PID controller, how we do that. That is going to be your assignment for the week. So moving back. Okay. So yes, well, that was something, wasn't it? We were able to simulate our boat in the Simulink through the PID controller system that we have learned so far. So today we saw how we simulated it in the software, and how it was able to remove out the error to the angular feedback that we gave to it. So well, any guesses what we are going to do in the fourth week to our boat? Any guesses, anyone? So we now have seen how we employed the PID control system to the board, but any guesses what we are going to do in the next week, in the next webinar that we have? Any wild guesses are welcome. Not a problem. Do I see any guesses? Okay, so in the next week, as we have seen the implementation of PID in as far as our board is concerned that we made, the next week we will be implementing more things in it, like the LQR system that we earlier learned, and how it stabilizes it betterly than the PID system that we are using right now, and like more advanced controls on the controlling of the system and bringing it back to the balance. So yes, that was my time, guys. I'm is my contact number, so you can always contact me for any queries, any doubts that you had pertaining to this week or studying the assignment. I will be there throughout the bootcamp to help you. Yes, that will be all from our side. Thank you everyone for listening to me. If you guys have any doubts, any queries related to any topic, you can just tell me right now. Related to the simulations that we saw, or the MATLAB and Simulink portion that we had, the slides part earlier, where we explained how the different systems that we have learned so far, now they were applied to the board.